So I'd like to thank the organizers for the opportunity. So today I will talk about some recent work with Eckhart feedback. This is about characteristic foliation, and it has to do with projective symplectic geometry. So I realized that I gave a talk about this a few weeks ago in an algebraic geometry meeting, and realized that people are not so familiar with this word foliation. So I will start with explaining what this means. And also some people are not familiar with the symplectic manifold, so I will explain what this means. And then I will explain what the problem is. And the actual solution of the problem is rather easy. So the important thing is to understand the concept and why this kind of problem is interesting. That's more important for today's talk. So let me start with the definition of foliation. This is something rather standard in differential geometry, but also I think in algebraic geometry, but apparently it didn't appear in any textbook. So that's the problem. So today we will consider a very simple case, just rank 1 foliation. And rank 1 foliation is particularly easy to describe. So rank 1 foliation on a smooth variety just means a line subbundle of the tangent bundle, in the sense that its quotient is also locally free. So in other words, at every point you are given a one-dimensional subspace of the tangent space. So such information, of course the assignment must be algebraic, so such information is rank 1 foliation. So it's just a line subbundle of tangent bundle. Now another way of describing this rank 1 foliation is by the following exact sequence. This exact sequence where this is a sheaf of differentials on the smooth variety, and it's given by the dual of this. So it's given by a rank 1 quotient. So here F is an invertible sheaf, and omega is also locally free, and it's a rank. The rank is a dimension of x minus 1. So whenever you are given such exact sequence, this is rank 1 foliation. Now when you say foliation, you want to study in the following geometry way. That's why we call this foliation. I mean, otherwise it's just maybe we call it like subline bundle or tangent bundle. But instead of this, we say it's foliation because we like to study the following geometric object is leaf. So what is a leaf? Leaf is a Riemann surface. So this is not an algebraic object in general. So, but over complex numbers, whenever you are given such a foliation, there's a leaf through every point. So a leaf means for given point, the tangent space of this Riemann surface, this one-dimensional guy, is exactly this given direction at that point. So in other words, the tangent to this Riemann surface is exactly annihilated by this Q. Then we say that this is a leaf. So well, I don't know, but for me it's just better to consider foliation as something like this. So it's given by some Riemann surfaces through every point. In such a way, this X is just a disjoint union of all these leaves. But these are all holomorphic objects. So these are Riemann surfaces. And the way it is put together is exactly algebraic in this sense, that the tangent directions are exactly algebraic line bundle inside the tangent bundle.
Is it equivalent to giving a vector field?
It's not exactly equivalent. Yeah. It's equivalent to giving a twisted vector field up to some twisted by line bundle.
These joints, Riemann surface,
Yeah, these are disjoint because this is regular everywhere. So everywhere is smooth as a complex manifold, as a Riemann surface. It's smooth everywhere at every point. But it's completely, perfectly possible that they may be dense.
What about P2? It does not have any foliation?
P2 doesn't have such nice foliation. It doesn't have. So there are foliations with singularity. I mean, there are various notions, but today we only consider regular foliation. So everywhere regular foliation.
So here you mean the Riemann surface can be non-compact?
Yeah, non-compact, usually non-compact. And here, by Riemann surface, what do I mean is as an abstract Riemann surface embedded. So it can be, it need not be closed. But soon, you don't have to worry about this soon. You will see, at least today. It's a big problem in foliation theory, but today we are not going to worry about this. Because we will consider this case. So such rank 1 foliation on a smooth variety is called an algebraic foliation if all of its leaves are algebraic curves. So if these Riemann surfaces are really algebraic curves, then we say that it's algebraic foliation. And our main concern is algebraic foliation today. So you don't have to worry about the transcendental case too much. But still, let me give an example. So you consider an abelian variety as quotient of the vector space by a lattice. Now choose a line, one-dimensional subspace of the vector space, and then you consider its translations of this line, and then they descend to a foliation on the abelian variety. So because this gives us line subbundle of the tangent bundle, which is trivial. So this way you get the foliation. Now if this line contains a non-zero lattice point, then this is algebraic foliation. Otherwise it is not. So this is an example showing on abelian variety there's foliation, which sometimes it becomes algebraic, sometimes it's not. Another example. This is the most trivial example. Suppose you are given a smooth morphism, smooth projective morphism between smooth varieties of fiber dimension 1. Then certainly the fibers of F, this determines an algebraic foliation. It's just to, I mean, in this case, this exact sequence just means that this part is just, this Q is just a pullback of the sheaf of differentials on B, and this invertible sheaf is nothing but the relative dualizing sheaf of this curve fibrations. So that's the situation. So example 2 is a kind of a trivial situation of foliation. In this case, there's nothing to study anymore, as a foliation is almost as good as you want. The worst thing is, of course, non-algebraic foliation. But today you are interested in algebraic foliation, but which is not of this type. So there's some hierarchy of complication. The simplest one is this. Worst case is completely transcendental ones. But there are algebraic foliations which is not necessarily of this type, and these are not very well understood. Anyway, that's about foliation. Now I'll explain the symplectic geometry a bit. Let's start with symplectic form. This is something we saw this morning in Song's talk. But let me recall the definition. So symplectic form just means two form on a vector space, namely an alternating antisymmetric form on vector space V, such that, and we say that the kernel of this two form is defined by this, that it's just those parts where this is degenerate. And such a two form is called the symplectic form if the kernel is 0. So if it's non-degenerate two form, then we say it's symplectic form. this easy to see that if a vector space has a symplectic form, then it must have even dimension. Now, suppose you are given a symplectic form. Let's choose a hyperplane. So dimension 2n minus 1. Then if you restrict the symplectic form to this hyperplane, then the corner is exactly as dimension 1. This is easy to see. Well, maybe this is what you learned in undergraduate, some algebra. So because it's non-degenerate, it's exactly dimension 1 for any hyperplane. Okay, so now I'll define symplectic manifold. So suppose you are given now a holomorphic 2 form on an even dimensional complex manifold. Then we say that this is a symplectic form on this manifold if the restriction of this guy to each tangent space is symplectic. On this vector space is symplectic. Then we say that this is a symplectic form on the manifold. And the pair, an even dimensional complex manifold and a symplectic form on this manifold is called a symplectic manifold. So to be precise, maybe we have to call it a holomorphic symplectic manifold, because usually symplectic manifold refers to real situation. But today I just use this term, symplectic manifold. Now, if moreover this M, this complex manifold, is a projective variety, then we say that this is a projective symplectic manifold. So let's give some examples. This is a trivial example. You choose an abelian variety, even dimensional abelian variety. Now you pick a linear coordinates P1 to Pn and Q1 to Qn on this 2n dimensional complex space. And then we have the following symplectic form on this vector space, given in terms of these coordinates as this expression. So this is a symplectic form on the vector space. Now it's invariant on the translation, so it descends to a symplectic form on the abelian variety. So any even dimensional abelian variety has such symplectic form. So even dimensional abelian variety is an example of projective symplectic manifold. Of course, you can choose this in many ways, but they are all up to on C2, and they are all equivalent to this. But they are different. The choice, depending on the choice, you get different ones on the abelian variety. Another example: if you have a projective KAIST surface, then the canonical boundary is trivial. So there is a non-zero section. But this means you have a non-zero 2 form, and this is nowhere 0 because it's trivial. So this gives a symplectic form on the surface. So a KAIST surface is an example of projective symplectic manifold. More interesting examples are given by Hilbert schemes. So for fixed projective KAIST surface S and positive number n, we consider the Hilbert scheme of n points on the KAIST surface. Then this is a 2n dimensional projective symplectic manifold. And the symplectic form, there's a canonical symplectic form induced by this symplectic form on the KAIST surface. So this is also well known. So these are examples of projective symplectic manifold. Now I will define what's the relation between, and what's foliation has to do with the symplectic manifold. This is the characteristic foliation of a hypersurface in a symplectic manifold. So let's consider a symplectic manifold. For example, I forgot projective. So let's consider projective symplectic manifold. 2n dimensional projective symplectic manifold. Suppose you are given a hypersurface, smooth hypersurface inside the symplectic manifold. then at every point, the restriction of this symplectic form to the tangent space of the hypersurface, this has one-dimensional kernel because this tangent space of the hypersurface is a hyperplane inside the symplectic vector space of the tangent space of M. This has to be, yeah. So the notation is, this is tangent space of X. So at every point of X, there is a distinguished line one-dimensional subspace in the tangent space. So this way you get a line subbundle. So in other words, you get a foliation of rank 1 on the hypersurface. And this is called the characteristic foliation of X. So whenever you are given a hypersurface in a symplectic manifold, you have automatically a natural foliation on the hypersurface. This is characteristic foliation. Now the main question you are interested in is the following. So given a projective symplectic manifold, M, and the smooth hypersurface, X, so you ask the question, when is this characteristic foliation on algebraic foliation? Now this kind of question in algebraic geometric setting, as we formulated here, has not been studied very much. It only, I think, drew people's attention very lately. So there's almost no work. So I will essentially tell you about all the works on this. But in real symplectic geometry, this was a very old question and one of the central questions, because this has to do with these characteristic foliation in real symplectic geometry is exactly the orbit of motion in the setting of classical mechanics, celestial mechanics. When you interpret classical mechanics as in terms of symplectic geometry, a hypersurface means some choice of energy functional and energy level set, and characteristic foliation is exactly the orbit of motion. So whether the characteristic foliation is algebraic or not has to do with whether the orbit of motion is periodic or not. So it's a very old question, as old as Newtonian mechanics. So in real symplectic geometry, this has been studied a lot, and there's a central problem. But somehow in algebraic, in complex symplectic geometry, it has not been studied very much. But it's a very natural question.
Is there any relation with the hypersurface and the leaves of characteristic foliation? The Riemann surface and the hypersurface?
Yeah.
Has some relation, or is it
yes.
geometrically?
I mean, first of all, this characteristic foliation is determined by this hypersurface this way. But you can write down, when you are given a local defining function, you can write down a differential equation for this in terms of the local function. It's, I tried to write it down here, but then I thought that some people don't like differential equation, so I skipped it. But it's not difficult. If you are given expression for the symplectic form and expression for the local function, then you can write down this characteristic foliation as a local vector field explicitly. Yes. Now here's one of the results that I recently proved with Ogiso. So this, I cannot define this exactly today, but it means that some of the symplectic manifold has a natural fibration called Lagrangian fibration. And if you look at the discriminant hypersurface of such fibration, it means that the singular fibers, locus of singular fibers, this is a hypersurface. And the characteristic foliation of such hypersurface is always algebraic foliation. This is something we proved recently. So this is one example of a rather general class of hypersurface where you have algebraic foliation. Now there are some other examples of hypersurfaces, very explicit examples with algebraic characteristic foliation in a recent preprint of Justin Sawan. But I think these are all the works on this problem. at least which appeared. Now, one strange thing is there's no example of hypersurfaces with non-algebraic characteristic foliation so far. And there was a conjecture I made with Ogiso that the characteristic foliation of a general hypersurface in a projective symplectic manifold of large dimension at least 4 is not algebraic. So because this hypersurface seems to be very special nature in the examples, the hypersurfaces with the algebraic characteristic foliation have some special properties. So we thought that if you just choose a general hypersurface in reasonable sense, then it must not be algebraic. The characteristic foliation must not be algebraic. That's the conjecture. And this is the main result today. So it's a result I recently obtained with the feedback. So suppose you choose a smooth hypersurface which is of general type in a projective symplectic manifold, dimension at least 4. Then the characteristic foliation of X is not algebraic. So I think this is the first example of such hypersurface with non-algebraic characteristic foliation. The problem is, to show that some foliation is algebraic is, in a sense, easy, at least philosophically, because you just write down the foliation explicitly and show that the leaves are algebraic curves. This is easy. But to show that something is not algebraic is not easy, because you cannot prove that something is not transcendental. You have to eventually you have to get some contradiction out of something. So it's such a problem. So this kind of verifies the previous conjecture, because as long as you choose a hypersurface of general type, then it's not algebraic. But examples are provided by any ample hypersurfaces. So if you choose a smooth ample hypersurface in this projective symplectic manifold, then its characteristic foliation is not algebraic. And the reason is by the adjunction formula that for symplectic manifold, because of the symplectic form, the canonical boundary is trivial. Now by adjunction formula, if you are given an ample hypersurface in a symplectic manifold, then the canonical boundary of the hypersurface is ample. So any ample hypersurface must be of general type. So this comes from the statement that any hypersurface of general type has non-algebraic characteristic foliation. So this way you get many examples of hypersurfaces with non-algebraic characteristic foliation. So let me give one corollary of this. So here I said example, but it's corollary of the theorem. So let's choose even dimensional, principally polarized abelian variety with a smooth zeta divisor. So assume that this is smooth, zeta divisor is smooth. So this is true for general choice of principally polarized abelian variety. Now you pick any linear coordinates on the vector, even dimensional vector space, and then we have the zeta function defining this zeta divisor associated with the given period. So this is now entire function on this vector space in these coordinates P and Q. Then if you choose a general point on the zeta divisor, the solution to the Hamiltonian flow, this is what's called the Hamiltonian equation in mechanics. So this kind of differential equation has solutions through every point, and any solution of this differential equation through a general point cannot descend to an algebraic curve. Now this is because this is the expression for the characteristic foliation, which I avoided before. So this is how you write down the characteristic foliation in terms of the defining function. as a Hamiltonian flow. So, but this here I wrote it down because this is a very explicit situation. You are given an explicit entire function, and you can explicitly write down differential equation, and you are interested in whether the solution of this differential equation descends to algebraic curve or not. And here the theorem says that this does not descend to algebraic curve. And although this is very explicit statement, I don't think it's known before. Okay. Now I have to explain litaka dimension. In the previous talk or portion, he called this Kodaira dimension. So I had no time to change it. So you have to accept hopefully it's not confusing. So for given invertible sheaf F on a smooth variety, if it has some section after taking some power, then we say that the litaka dimension of the invertible sheaf is the integer k, which measures the ratio of growth of the sections as we take tensor power of the invertible sheaf. But this is exactly the same as what Kosha defined as the Kodaira dimension of the invertible sheaf. Now this is a very simple thing. So if you have a surjective morphism between two varieties, the litaka dimension of the pullback is at least as big as the litaka dimension of the original one. It's kind of trivial. Now we say that invertible sheaf is big if its Kodaira dimension is equal to the dimension of x. And then it's easy to see this also. Suppose you are given a morphism. If the pullback of some invertible sheaf is big, then this implies that the morphism must be generically finite over its image. Because to be big, it has at least as large as this growth, but which means that it's generically finite. Okay, so the reason I introduced this litaka dimension is to reformulate this result with the feedback. Because the problem is when we first considered this problem, it was not clear how to approach this. But once we formulate the correct, more general problem, then it becomes very easy. This as usual in mathematics. So it's usually easier to prove something something better. So the situation is you have to relate it to this litaka dimension of something. And this is the result. It's theorem on litaka dimension for foliation. So this has nothing to do with symplectic geometry. Just given any smooth projective variety, suppose you are given a foliation of rank 1, like this. If this is an algebraic foliation, and if this f is big, namely its litaka dimension is equal to dimension of f, then the litaka dimension of determinant of this Q is at least as big as dimension x minus 1. So if this part is big, then this part is pretty big. That's what it says. But under the condition that this is an algebraic foliation. Now this is not true if it's not an algebraic foliation. So it's rather strange that being an algebraic foliation or not affects the litaka dimension this way. So whenever you are given such a foliation, being algebraic implies this property, the relation between litaka dimension of this guy and this guy. So this seems to be crucial. And we can see that this implies the other result as follows. So suppose you are given the characteristic foliation of a hypersurface. Now, so you have the sequence and given by hypersurface in a symplectic manifold. In this case, the symplectic form on here descends because f is essentially given by the kernel of the symplectic form restricted to x. The symplectic form over here descends to a symplectic form on Q, in the sense that it's non-degenerate everywhere. On the other hand, F is equivalent to the canonical bundle of X, because by adjunction formula, and M has trivial canonical bundle. Now, if X is general type, then F is big. But determinant of Q must be trivial because there's symplectic form. In other words, the litaka dimension is 0. So this is a contradiction to our theorem. This is big, but this has litaka dimension 0. So where is the contradiction? The contradiction is if we assume that this is algebraic foliation, then it gives such contradiction. So this shows that the foliation is not algebraic. So the theorem on litaka dimension of foliation implies the non-algebraic theorem for characteristic foliation on hypersurface of general type. But also this shows that the condition of algebraic foliation in this theorem on litaka fibrine is necessary condition. So without this algebraicity assumption, the bigness of this doesn't imply that this litaka dimension is large. So it's perfectly possible. So here we give examples where F is big, but this has litaka dimension 0, and foliation is not algebraic. So this condition of being algebraic foliation is really necessary in the theory. Okay. Now I'll show one special example where you can apply this theorem. Because you may ask whether there are really such cases, because we just showed that in the case of characteristic foliation on general hypersurface, it's not true that it's algebraic. So rather there's a situation where the statement of this really holds. Are there examples of such situation really? Well, there are many examples, and so I will show this example. So the example comes from universal family of curves over moduli space. So just to have a fine moduli space, we give some level structure. So we have a family of curves over the moduli of curves. And let's denote by omega f, the relative dualizing sheaf of this family. Now choose a smooth projective subvariety inside the moduli of curves and consider its inverse image. Then this is, you have this fibration, so it has algebraic foliation, as I explained. This is trivial foliation, just given by the fibration of smooth morphism. So, and the fibers are just curves. And in this case, as we saw before, this F is the relative dualizing sheaf, and Q is the pullback of the sheaf of differentials. So here's the picture. So here I have a universal family of curves over moduli of curves. I just choose some submanifold inside the moduli of curves, and then consider the fibration over this. Then these give foliation on this projective manifold X. Now, to see that in this case satisfies all the conditions of our theorem, we use Fiebeck's positivity theorem, which was also recalled in Kosha's talk. So this is but the simplest case that when you have a universal family of curves, the higher direct image sheaf is ample as a vector bundle if nu is at least 2. And using this, we can show that this sheaf F, the relative dualizing sheaf, satisfies that this is ample. So since it's the projective normality of this relative dualizing sheaf on each fiber, this implies that F is big. So in this case, F is big, satisfying the condition of the theorem. So this way you can easily find many examples where our theorem applies. But although these are all trivial foliation, these are just given by fibration, but this provides many examples where we have algebraic foliation where F is big. Now in this particular special example, it's easy to prove the theorem. So this is well known, but let me give you record the proof. By Kodaira-Spencer theory, well, maybe for curves it's even more elementary, but anyway, the direct image of relative dualizing sheaf is exactly the sheaf of differentials of the moduli space. The quadratic differentials are sheaf of differentials of moduli space. And by Fibek's positivity theorem, this implies that this is ample. So, but this fact is well known, I think. The cotangent bundle of moduli of curves is ample bundle. Now, by our construction of a special example, we chose this B as a submanifold inside the moduli space, which means that its sheaf of differentials is ample. But our Q is pulled up of this. So the determinant of Q, the itaka dimension of determinant Q is equal to itaka dimension of determinant of this omega 1B. But since this is ample, this is big on X. So it's big on B. So this has dimension X minus 1. So this way we see that the theorem holds in this trivial example. So the main problem is whenever you have, so here we saw that when you really have a nice foliation, in the sense that it's really fibration, then it's easy to see the theorem, essentially. So the difficulty is a general foliation is not really fibration. That's the main difficulty. So how to understand the structure of general foliation. So how far is general foliation from smooth fibration? That's the main question. Okay, so that's the question. How far is the general foliation from a smooth fibration? Now, one typical difference is, suppose you have a fibration which has multiple fiber. Now, as a fibration, it's not a smooth fibration because of the multiplicity. But as a foliation, it's really very nice foliation. At every point, there's lines of bundle everywhere. So this is a typical difference between foliation and fibration. So as a fibration is bad, but as foliation is very good. Now, how to handle a situation like this? Quite often, we know that you can remove multiple fiber by taking some atal cover, by taking the branched covering of the base. You can sometimes just, by atal covering, you can remove the multiple fiber, this semi-stable reduction. So this is something we can say. So up to atal cover, it becomes very nice now, really smooth fibration. So one may ask whether this is always true, that when you are given foliation, can you take some atal cover to make it smooth fibration? Then it will be very nice. Now this is not true in general. So when you are given general foliation, you cannot just take atal cover to make everything into smooth fibration. This is not true. But it's true locally. So that's the result. So this is called the Reeb stability theorem. So here's the statement. Suppose you are given an algebraic foliation on a projective manifold. Then for each leaf, you can choose a neighborhood, Tarski-open neighborhood, and an atal covering, and with a smooth projective morphism, or fiber dimension 1. So this is now really smooth fibration, such that these leaves of this, these fibers of this smooth fibration go to leaves of the foliation in U. So locally, after taking atal cover, you can make the foliation into smooth fibration. So that's the Reeb stability theorem. I think this should be somewhere, but we couldn't find the reference. But anyway, this can be proved. We prove it actually using Reeb stability theorem. There's a corresponding statement in differentiable topology, that when you have a differentiable foliation with compact leaves with some properties which hold in algebraic situation, you can always do this. Once you know that you can do this differentiably, then you can give all these structures and make it into algebraic setting. That's not difficult. So we generalize this result from topology into algebraic setting. So this is a local Reeb stability. I mean, the name Reeb stability comes from this Reeb. He is a topologist. So it's at least locally up to ethyl cover, any algebraic foliation can be made into smooth fibration. Now, one question I'd like to ask is whether it's possible to prove this algebraically, because the proof we gave is use this topology. But it should be possible, but I don't know. I don't know any reference where I don't know any proof, any algebraic proof of this. Now, this is nice, but the problem is this local. So only locally you can do this. On the other hand, our theorem is global nature. It's about litaka dimension, so we need something global. And we want to extend this to a global situation. How to do this? First of all, the local Reeb stability theorem gives us some cycle map. So in the following way. So for each leaf, we associate its multiplicity as the minimal degree of this ethyl cover appearing in Reeb stability as the multiplicity MC. And then for general leaf, it's just 1. Because for general leaf, you don't have to choose any ethyl cover. But for special leaves, it's roughly speaking, it's the multiplicity of the corresponding multiple fiber. And then the Reeb stability, because it's locally always true, it shows that if you assign for each point x, this cycle, MC, the cycle of the leaf with this given multiplicity, then this gives a morphism to the Chow variety of x. So this local Reeb stability can be put into the following commuting diagram, that we choose some open set, and it's ethyl cover, and this is a smooth morphism. Now we have a morphism to the Chow variety, so that this commutes. So this exactly corresponds to the previous picture, that sometimes you can remove the multiple fibers by taking ethyl cover, but on the base it's not ethyl usually. It's usually branched covering. But anyway, you put it now in the form you are familiar with. So this is removal of multiple fibration, essentially. Now we want to put all these guys together into a global picture. But this is also not immediate. The problem is they may have all different degrees depending on the open set. And how to patch them in a consistent way. This follows from the following. So first we need some universal family of curves. So we need to give level structure. So this is a standard result that for any integer n, if you are given a smooth family of curves of genus at least 1, then no, bigger than 1, then after base change by ethyl cover, you can give a level structure. In other words, after taking ethyl cover, you can make it coming from universal family. So after taking ethyl cover, this family just comes from pullback of the universal family by a morphism with a base into the moduli space. So this is just a technical point, but necessary. So in our situation, when we have this Reeb stability, so we take some ethyl cover so that it becomes a smooth fibration. Now we want to give this smooth fibration some level structure by taking an extra ethyl covering. So we can assume that in the Reeb stability, under this ethyl cover, this smooth family of curves actually have level structure. So we may assume this. And then we can now put it into the following diagram. So here you have the map to the cycle map, and here we have this local ethyl covering. But then we can this way, by putting the level structure, you can say that this comes from fiber product from the universal family. So in this way, we can kind of modulate this local information to put them together into global picture. So you have just finitely many of these open sets cover X, and then you take a fiber product and so on, and all these are controlled because over here is global and over here is also global. So they are controlled completely. So they patch together very well. So this way you can globalize the Reeb stability theorem. So here's the global Reeb stability theorem. So this is a statement about algebraic foliation in general, whose Reebs have genus bigger than 1. So suppose you are given algebraic foliation with Reebs of genus bigger than 1, then you can always put them into the following picture, in the following diagram. So here V and W are projective manifolds, smooth varieties, and sigma is generically finite, and this is fiber product. So this family really comes from the universal family. And our foliation is related to this as follows, that the pullback of this guy, the lift of this guy F to here is the relative dualizing sheaf of the universal family of curves, and the lift of this guy contains the pullback of the sheaf of differentiable W. So this means that up to some covering, this becomes smooth fibration of curves, very nice smooth fibration of curves, but it's not an ethyl cover really. I mean, this sigma is not really ethyl because this is branched usually, and but it's kind of locally ethyl, so it's somewhat it's locally factors through ethyl cover. So the structure is not. This doesn't give a very simple structure theorem about algebraic foliation. This is a kind of substitute. You cannot really make everything into smooth fibration after ethyl cover. But after some covering, it becomes smooth fibration, and it factors through ethyl cover locally. So locally, as we saw before, locally is after ethyl cover, it becomes smooth fibration. Globally, it becomes smooth fibration after some branched cover. So it's a slightly technical situation. But this is all we can say in general about the structure of algebraic foliation by curves of genus bigger than 1. But this is a quite general statement. Now, using this global structure theory, it's not difficult to prove the theorem. So let's give the proof. So we have this situation where we are given foliation, and we have this diagram where F is now pullback of the relative dualizing sheaf of the universal family, and Q, if you lift Q here, then it contains the sheaf of differentials, and they have the same rank. Now suppose you assume that this F is big, but then it means that the pullback, the lift to V is also big. So in other words, the pullback of the relative dualizing sheaf of this universal family is also big. But then, as we saw before, this implies that this eta is generically finite over its image. Because the pullback is big, it must be generically finite. Then, since these are all smooth morphism, F and this F, these two are smooth morphisms, if this is generically finite over its image, that this also has generically finite over its image. So the pullback of the sheaf of differentials on the moduli space to sheaf of differentials on W, this is generically surjective. But then implies that since we know that this is ample, this implies that the litaka dimension of determinant of this guy is at least as big as dimension of W. And then finally, since it contains the pullback as a subsheaf of the same rank, the litaka dimension of Q is the same as this. This way we finish the proof. Okay. So that's the end of the proof. Now finally, I'll give some open questions. The obvious question is how much singularity can we allow on the hypersurface? So we assume that it's a smooth hypersurface in a symplectic manifold. But suppose you have a singular hypersurface, ample single hypersurface. Does it hold? So suppose you are given an ample hypersurface in a projective symplectic manifold with some mild singularity. Now, is the characteristic foliation on the smooth part, is it non-algebraic? This we don't know. Of course, if the singularity is like immersed, then our proof works. But otherwise, it doesn't work. Another question is, what about special leaves? Namely, we show that it's not algebraic, but it may be possible that at least some leaf is algebraic curve. So these are most leaves are transcendental, but then there may be some algebraic leaf. Nobody knows. So even for these cases, we show this. What we showed is that some leaf is not algebraic. That's what we showed. But we don't know whether all leaves are not algebraic or some leaves may be algebraic. So this is a question, but this is certainly is a much more difficult question. And our method certainly doesn't apply in a question like this. Now these two questions I think is open even for Theta divisor on abelian variety. The explicit situation I mentioned as a corollary. So even in this case, if the Theta divisor is singular, we don't know what happens. And even when the Theta divisor is smooth, we don't know whether there's some compact leaf of this Hamiltonian flow or not. We have no idea. So these are open questions. I have to finish a little bit early. Thank you.
Any questions?